started. So our next talk will be on secret key PIR from random linear codes by Kai, Yuval, Tamer, and Alon, and Tamer.
Thanks, Daniel. So the talk will be on secret key PIR, joint work with Saisai, Yuval, and Alon. So let me start. So what is PIR or PIR? So that's private information retrieval. So we're thinking about a setting where we have a client, we have a server. The server has some database with n elements, and the client wants to get some element, okay? So indexed by some I, and we're doing crypto, so we want to hide this I from the server. So we want to get the element without telling the server which element we are getting. Good. So to formalize security a little, not very formal, but still, we want that. So good. So if the client is generating the query with some query algorithm Q, then I want that a Q of I is indistinguishable from, say, Q of 0, okay, for every I. And of course, the server will not reply by the element, but rather by some answer, and which the client will be able to decode. Okay. And the historical goal, at least for PIR, was to get low communication. So if you think about it a little, you see that it's trivial to get PIR with communication n. The server simply sends the entire database. And the goal is to get sublinear communication PIR, and any sublinear communication is already non-trivial. Good. So PIR is already almost 3 decades old problem. And we know a lot about it. We know how to construct PIR with communication that is asymptotically polylogarithmic in n from many, many standard assumptions. So we know to build it from lattice-based assumptions, from number theoretical assumption, but one missing category of assumptions here that is kind of prominent in crypto is coding theoretic assumptions, like LPN, okay? So this already hints where I'm going. But maybe a bigger problem with these protocols is that although they get very nice asymptotics, they're not very practical. And one reason for that is that the server work, the amount of computation that the server has to do to respond with the answer is it grows with n and even more. And this is kind of inherent. In this plain model, if the server, if there exists an element that the server doesn't touch, then the client, then can he know that the client didn't request that element? So we can easily show that the server has to at least scan the entire database. And this makes PIR in this plain model maybe inherently not very practical. And for this reason, people have considered different models, specifically what I'm going to call PIR with preprocessing. So here, there are 2 phases, the offline phase and the online phase. In the offline phase, I allow the client to encode the database using some encoding. So I'm going to denote it here by x hat, and I allow it to be a little larger even than the database. But after this offline phase is complete, the client can forget about the database and its encoding. It's all in the server. And now he can query the server like he used to do with queries, get answers, and retrieve any element he wants privately. And I still require the same security notion. 3 years ago, there's been this amazing breakthrough. And I'm not saying that only because Daniel is here. So they build what's called double efficient PIR, okay? So what's double efficient PIR? Double efficient PIR is PIR where also the server, and not only the client, is super efficient. And what do I mean by that? I require it to be sublinear in n. So the server no longer has to scan the entire database. And in fact, what they show is that you can do that with polylogarithmic server compute. Good, this is great asymptotically for STOC. But this is not very practical, okay? In particular, the storage size or the size of the database encoding is much larger than n in practical terms. So we have a polylog n overhead in storage. Good, so this state of affairs leaves us with few questions that we're gonna address today. The first is whether we can build PIR from standard coding theoretic assumptions. Again, let's take LPN, for example. LPN is a pretty standard assumption by now. We know how to build public key encryption, CRH under some parameters, but we still don't know how to build a PIR from LPN. At least not very impressive PIR. We do know how to build slightly non-trivial PIR from LPN. And not very, let's say, not the most standard version of LPN. Another question that is maybe more relevant for practice is whether PIR can be practical. And I'm saying practice a lot here, although it's we're in a theory conference. But what this work is offering is a new theoretical framework that would give new, very practical solutions. Even in the pre-processing model, we still don't know PIR protocols that are practical, that don't require the client to have large memory or a large state that he maintains over time. Okay, so such solutions are maybe less attractive. Okay. So we address these two questions, and we address them positively, but in what we call the secret key PIR model. Okay, so what's that? This is not a new model. It's been introduced 9 years ago, but let me tell you about it. So it's very similar to the first PIR with preprocessing model that I showed you, except here now I assume that the client has some secret key. And the database encoding depends on this secret key. Okay, so now I have subscript secret key here when I'm encoding the database. But again, after the database is encoded, the client can forget about it and only store his 128 bits of secret key. And then in the online phase, he can still query the database, again using the secret key, and get an answer and decode it using the secret key. One weakness maybe of this model, which I will get to, is that here the database is in a sense owned by the client, as opposed to the other models that I showed you, where the database is actually can be thought as being owned by the server and it's public and any client can access it. Here I ask that the client is encoding the database using his secret, and then he can access the database only using his secret. Good, so I told you that this model was introduced some years ago, and this works. They could also build double efficient secret key PIR from non-standard assumptions. Again, very nice asymptotics, not very practical. Let me just position a little, like give you some idea where secret key PIR sits among other cryptographic primitives. You can think about it as some version of searchable encryption that doesn't leak the access pattern to the data. Okay, so it's like searchable encryption, but with no security leakage. Another way to think about it is as read-only oblivious RAM, where there's no state that is maintained neither on the client side nor on the server side. Lastly, I want to say that since the client only has a small secret key and not a state that he has to maintain, this can be great for MPC to plug in some MPC protocols and add MPC applications to either distribute the client in some sort of public database situation and so on. And last thing I want to add is our results also extends to other models of PIR where actually the database is public or owned by the server. So that's a model where I'm going to show you today our results, but our results are not restricted only to this model. Okay, so let me be more specific about what we get. In general, we present a new paradigm for building PIR, or secret key PIR, from code-based cryptography. And what do we get from that? No, okay. We get secret key PIR with communication into the epsilon from LPN, and not any LPN, but LPN that we don't know implies public key encryption even. To be more specific, we can assume LPN with any inverse polynomial noise. So this strengthens period evidence that secret key PIR doesn't require public key encryption. And in fact, it inspired, I think, subsequent work that actually showed that secret key PIR with square root n communication is implied by one-way functions. So this is a much more generic security assumption, but it takes you only down to square root n communication. And it's not clear how to get n to the epsilon. Another sequence of our framework is a very efficient secret key peer protocol. And what do I mean by by very efficient? In this protocol, the database encoding size is almost n. So you almost don't have storage overhead. And not only that, the circuit size that describes the server computation is almost 4n. So it's not much larger than optimal. And we get that from new assumptions that I'm gonna tell you about later on. But for now, I'm just gonna say that they are variants of a hardness assumption that was introduced in 2009, which is called learning subspace with noise. Okay, so this is the first peer in any model with preprocessing where the server circuit has linear size. And this gives us a new perspective on double efficiency. Previously, double efficiency considered the RAM model for server computation. But you can ask why all of a sudden I care about circuit size. First of all, it's a nice theoretical question to think about. But second, we showed in follow-up work that circuit size actually can be very relevant for practice as well. Okay, so we showed that similar protocols can give you very efficient ways to perform encrypted matrix vector product that can have also applications in encrypted inference and so on. Good. So now that I told you about the results, I will tell you a little on how we get them. So again, we have client, a server. The client wants to retrieve the ith element. And for now, let's not worry about the client's complexity because there are generic ways to deal with it. For now, I will be worrying mainly about the server's complexity. And this includes the computation, storage, and server-to-client communication. And I'll start by representing the peer functionality using a very simple linear function. So to retrieve the ith element, the client could potentially send the ith unit vector, and the server just performs inner product, which would be equal to the ith element. This is very efficient for the server in terms of circuit size, but obviously it's not secure. So we want to make it secure now. And the very simple idea would be to mask this unit vector. So I sample a random mask, I add it to the unit vector, the server does the inner product, but good, we don't get anything, right? Because we don't get exactly the ith element. There's this still term that we need to cancel somehow. So I want to enforce that this x times c, my database multiplied by the mask that I added, is somehow 0 always. And how do we do that? Our idea is to use dual linear codes that are secret. So we're gonna use database code that I will denote by D, and a query code that I'm gonna denote by C. And these two codes are dual. So if I somehow could encode my database using the code D, and the mask that I add to my queries using C, then XC will always be 0. Good. And I will at some point assume that these codes are systematic, so they will look like that. Good. So what do we do? So again, I let the client encode his data using the data code D. And then he uploads it to the server. So now the server doesn't has an n-size array anymore, but rather an array that's a bit larger. How much larger? We will go into it. And then the mask that the client previously sampled at random, he will now sample as a code word from the code C. So now it's no longer just a random vector, but rather a random vector from this low-rank subspace. And he does what he did before. And now we have that x times q is actually the ith element of x. Why? Because the codes are systematic. You do the math. Believe me, it's correct. Amazing. Okay, this doesn't look very secure. And indeed, one problem is that I told you that I'm trying to have two secret codes, but here the encoding x had already reveals the data code to the server. But for that, we have a simple solution. We just mask also the database by a random vector r. So now the code D is completely hidden from the server. But now we have this issue that the client needs to correct the answer by subtracting r times the query. So you might think we didn't do a lot here. Instead of the client multiplying the data by a unit vector, he's now multiplying a vector of the same size by his query vector, so we didn't save much for the client. But actually, R is just pseudo-randomness. It has nothing to do with the data, it's not structured, it's just pseudo-randomness that depends on the secret key that the client has. And for such vectors, well, I'm not being very precise here, but believe me that we have the technology to multiply pseudo-randomness by a chosen query. Good. So now we have this type of protocol where the codes are hidden. Good. The client is masking his query with some code word and getting the answer. And notice here that the server work is just slightly larger than n if the ratio between k and n, meaning the rate of the, it's a bit related to the rate of the code C. If it's low enough, then the server work is also not very high. Circuit size, very simple, it's just doing inner product. Good, so if we're able to instantiate this protocol, actually, we're getting something that's promising. The problem here is still security, unfortunately. So if we focus on what the server sees, he's seeing this unit vector plus C, and C is coming from this code. And this cannot be secure, right? Why? Because small c is always coming from a low rank subspace. So if you see k plus 1 of this, you can compute the rank, and you see that the rank is low, and you have an attack. So masking with C that is a code word definitely doesn't give you something that's pseudo-random. But we're used to this in crypto, right? We're used to algebraic structure, and we know how to hide it. So we can try to use LPN or LWE, add some Hamming error, get something that's pseudo-random. The problem with this approach would be that we no longer have correctness. It's never the case that such a vector with error would give us, would be dual to that, the data code D, so we will not have correctness. So the idea of this work is to just use different types of noise. What type of noise exactly? So first we look into a mixture noise. So now instead of adding just a low norm error to C, now I either give you C without any error or a completely uniform garbage. So it's either this or that. I'm mixing C with some uniform noise. So now I do have correctness with some probability. So if I add noise with probability mu, I will have correctness with probability 1 minus mu. And this is fine because we know how to correct errors in TCS. But this would get us some overhead in the data encoding size, because we would need to encode the data using error correction. And the overhead would be proportional to 1 over 1 minus mu. So the larger the noise, the larger the encoding. Makes perfect sense. And now C doesn't always come from a low rank subspace, but rather it sometimes comes from a low rank subspace. And now the question is whether this is secure. And you can already see some tension. The lower the noise, the better the overhead, because we need to correct less errors. But on the other hand, for security, you would guess that we need higher noise. We need to mix C with more noise to hide the algebraic structure. And now the question is, how do we choose mu? What does it have to be? So this problem of mixing code words with noise has been studied, like I said. It's been called learning subspace with noise, or LSN. It's been studied also, by the way, in learning theory, not only crypto. So we said that the efficiency and security of our protocol would depend actually on the choice of mu. So now let me tell you what is known about this. So we know that if mu is under some certain threshold, the problem is easy. It's not hard, actually. So, and we know that in some regimes, LSN is exactly LPN, so the two problems are equivalent. We show few reductions from and to LPN, and one of these reductions gives us our construction from LPN. And the problem with this reduction is that it assumes a rate that is very high, which gives us a very perhaps not very practical protocol, but that's how we get our feasibility result from LPN. I'll be quick now. To get our practical instantiations, we need to break this tension between security and correctness by proposing a different type of LSN, which applies different type of noise to the hidden subspace. And let me just tell you quickly how it looks. So now I'm sampling a code word C, and instead of mixing it with noise, I'm doing the following. I'll split it into blocks, and I will hide each of these blocks within uniformly random blocks. Okay, so the blue guys are random, the yellow guys are taken from C. And now I give you this, and we assume that this looks pseudo-random, or that this looks random. And we call this split LSN. So we conjecture that this is secure with constant rate, which gives us our 1 plus epsilon times n storage. And we prove it's secure against certain classes of attacks, including algebraic attacks. But of course, further cryptanalysis is needed. And we think this problem is very interesting to study. I'll finish here. Thanks for listening, and I'll take any questions. Thanks.
So I have a quick announcement. I'm from the organizing team. We keep our theory caravan moving into now online poster session that starts at 6:30 local, so in 25 minutes from now. This is going to be a fully online event on GatherTown. Instructions for these are already available on the program. We currently have 21 posters from STOC and Fox recent conferences. So each of these posters will be in a room. We are trying to mimic kind of the in-person, but through an online event. So please pass this information on to your colleagues and friends in other sessions so that they can participate. And I think one of the talks from this session is actually also presenting. So if you have questions, that's the right time to ask them. Thank you so much.